Hello everyone. Am I audible? Yeah. Hello everyone. Welcome to you all for this today's session, that is Wednesday E01, Graph and End-to-End Learning for Speaker Recognition. I am Madhu Kamble from Eurocom, France, and he is Johan from BUT. And without any further ado, let's begin for the session. Over to you, Johan.
Yeah, okay. So the first paper is called Reformulating DOVER label mapping as a graph partitioning problem. And it's by Desh and Sanjeev, Khudanpur. And Desh will present it virtually. And Sanjeev is here to answer questions, and also Desh, I think, so depending on how it works out. So over to Desh.
All right. Hello, everyone. Good evening. I'm Desh. I'm a PhD student at Johns Hopkins University. And my advisor, Sanjeev, who's attending in person, is right there in the room with you. So if you have any questions, you can ask after I'm done talking. I believe there's a Q&A at the end of the talk. And also, if you have any intensive discussions, you can also ping me later on email or talk to my advisor who's there. All right, let's get going with the talk. So this talk is titled Reformulating DOVER label mapping as a graph partitioning problem, and it deals with speaker diarization and ensemble of systems. And we'll go into that right away. Here is an overview of the talk. So what I'll do is I'll first summarize speaker diarization and some approaches for diarization, including clustering-based traditional approaches and some new end-to-end approaches. And then I'll talk about DOVER, which is a method that we proposed recently for ensembling diarization systems. This will bring us to the actual problem, which is called label mapping. We'll formulate it as a graph, and we'll show that the original DOVER algorithm was exponential, so it's not good. We'll then show a new solution, which is based on the Hungarian algorithm and which is linear time. Finally, we'll round up with a randomized local search algorithm, which approaches near optimality. And finally, I'll show some experimental results. Right. Let's start by motivating the problem. So what is speaker diarization? It is usually referred to as the task of who spoke when. So in this task, the input is a recording which can contain multiple speakers. It's usually between a minute and up to several hours long recording. The output that the system is required to produce is a set of homogeneous speaker segments. The task is made quite difficult by the fact that the number of speakers in the recording is not usually known beforehand. And also the recording itself may contain overlapping speech, noise, reverberations, and all that stuff. The existing methods of diarization are several. The most conventional methods involve some kind of clustering. So what is usually done is we take the recording, we break it up into small segments and obtain embeddings from each segment. These embeddings may be obtained through different methods like I vectors, X vectors, D vectors, and so on. And once we have the embeddings for the segments, we then cluster them using different clustering techniques such as agglomerative hierarchical clustering, spectral clustering, variational Bayes, and so on. After this clustering step, we then obtain a segment level assignment for the speakers, which is the diarization output. This can optionally be followed by overlap detection and overlap assignment, which would then assign overlapping speech to more than one speakers as well. This is the conventional technique that has been studied extensively in the last 10 years or even more, and has been shown to give good results. There's another new line of research which has become popular, which involves end-to-end trained diarization systems. So these are based on supervised training. So they are trained with simulated mixtures usually, and they include methods such as end-to-end neural diarization, popularly called END, region proposal networks, TSVAD, which helped the STC team win the Chime 6 challenge last year, and so on. What's special about these systems is that there is no additional overlap assignment step which is needed. So these methods inherently include overlap assignment by design. So now that we have so many different kinds of methods available, a natural question that we can ask is that how can we obtain the benefits from all these complementary systems? For example, as I mentioned earlier, the clustering-based systems are quite good as estimating the number of speakers in the recording, and the end-to-end systems are usually much better at assigning overlaps. So we would like to have a system which can combine the outputs of all these diarization methods. For example, ASR has such a method which is called DOVER and which has been used for the last 20 years or more. This brings us to DOVERLAP, which was the solution that we proposed for this combination question in IEEE SLT earlier this year. DOVERLAP was inspired by a similar technique called DOVER, which was a method introduced in ASRU 2019. But DOVER could not handle overlapping speech while DOVERLAP could. That was the key difference, and some other methods that I'll go into detail later. And overlap has been successfully used recently. In the recently concluded Die Hard 3 challenge, the top two teams, which were the USTC team and the combined Hitachi JHU team, both these teams used overlap to combine their diarization systems, and very different diarization systems, in fact. The USTC team combined clustering-based, DSVAD, and separation-based systems, while our team combined VBX and END systems. And they all performed much better than the single best system, which shows that the overlap indeed has has a number of advantages, including the fact that it's quite easy to use. This is all you need to use overlap. How the overlap works is by breaking down the problem into two stages. The first stage is called label mapping. It maps speaker labels to the same label space, which is followed by a label voting stage, which performs weighted majority voting among all the hypotheses. I'll go into the details in the next few slides. Here is an overview of what the overlap label mapping stage does. Suppose we have the outputs from two diarization systems, A and B. Since the diarization systems do not output absolute speaker identities, but rather relative speaker identities, we may have speaker labels which look like A1, A2, A3 from system A, and B1, B2, B3, and so on from system B. And we do not have any correspondence between the labels from system A and those from system B, which presents a problem if we want to combine systems A and B. To perform any kind of combination, what is required is that we need to map all these labels into a common label space. For example, in this figure, the labels from A and B have been mapped to the label space S, and you can see A1 has been mapped to S1, A2 to S2, and so on. And in the system B, B3 has been mapped to S1, B1 to S2, and so on. So we can see that the labels B3 and A1 have a correspondence here, and they have both been mapped to label S1. And finally, when we have such a mapped hypothesis, any kind of voting can then be done. The next stage in overlap is the overlap label voting stage. And what this does is it first divides the recordings from all the hypotheses. Suppose in this case, we have hypothesis A, B, and C. And for simplicity, we have assumed all of them just contain two speakers. And these speakers may be overlapping in the different hypotheses. We first divide all the recordings into regions, where each region does not contain any speaker change. So within each speaker, there is a consistent number of speakers. Once we have divided into these regions, we then estimate the number of speakers in each region by computing the weighted mean of the number of speakers in all the regions. So for example, in the region marked here, the hypothesis A, B, and C estimate to 1 and 2 speakers respectively. And so the final assigned combined output will also contain 2 speakers. We then assign the highest weighted n speakers in each region to that region, and which gives us the final Dover lap output. So by combining the regions in these 3 hypotheses, we obtain the final hypothesis, which is the Dover lap output. So that was a brief introduction about Dover lap, and we showed how the label mapping stage works and how the label voting stage works. We then get into a little more detail about label mapping, which forms the core of this particular talk. In particular, we'll ask 3 questions. What is the label mapping problem? How does Dover lap solve this problem? And can we do any better? Let's get into this. If we look at the label mapping problem from a graphical view, we can construct a graph of this sort. In this graph, suppose we have 3 hypotheses A, B, and C. We represent each speaker in every hypothesis through a vertex. So for example, if hypothesis A estimates 4 speakers, A1, A2, A3, and A4, all of them are now a node in the graph. And similarly for hypothesis B and C. Finally, we get a graph which has as many nodes as the total number of speakers in all the hypotheses. We then form edges between every 2 nodes which are not from the same hypothesis. So for example, we'll have an edge from A3 to B3, B3 to C1, A3 to C1, and so on. Note that there would be no edges between 2 speakers in the same hypothesis. We then assign edge weights to all these edges. And we assign these edge weights so that the edge weight denotes the similarity of speaker labels. So the edge weight X denotes how similar speaker A3 and speaker B3 are. This edge weight is computed using an intersection over union kind of equation. The formula is shown here. The delta here shows all the regions where A3 are active. So we look at all the regions, the intersection of all the regions where A3 and B3 are active over all the union of all the regions where they're active. And this gives intersection of over union, which represents how similar they are. Intuitively, you can see that if A3 and B3 are active in exactly the same regions, that means we should assign it a high score. And if you look at this, that means that the values of delta A3 and delta B3 would be exactly the same. And so this ratio would turn out to be 1, which is high. And on the other hand, if they are very different, or if they're totally different speakers, that means they are active in entirely different regions. There is no, they are completely disjoint. Then that means that their intersection would be empty. And so this ratio would turn out to be 0. So these edge weights fall between 0 and 1, and they denote the similarity of speaker labels. So how we can formulate the label mapping is that it shows an instance of a graph partitioning problem. What this means is this particular clique, which is shown in red, is a maximal clique. And it shows that the labels A1, B2, and C2 have been mapped to the same label. That means that these 3 speakers actually denote the same underlying speaker. So the problem then can be formulated as follows. We want to partition the graph into a set of maximal cliques, which maximizes the sum of edge weights within the cliques. So for example, we want to partition this whole graph, which is this combined set of speaker nodes, and each of these colored cliques denote 1 assignment of speaker labels. So we have partitioned this into 4 cliques such that the sum of edge weights in the edges inside the cliques is maximum. Intuitively, this means that since this edge weight is maximum, so the similarity of the speakers which have been assigned to the same underlying speaker is high, which is exactly what we want. in the label mapping. We want that if the two speakers in different hypotheses are very similar, they should be mapped to the same underlying speaker. We empirically saw that this problem, when formulated such, is correlated with obtaining a better DER. So if we denote, if the total sum of edge weights here is the weight of the solution, then as the weight of the solution increases, we found that the resulting DER of the solution of the combination also reduces. So as we go on having higher weight, we also result in a lower diarization error rate. And this is shown on some recordings obtained from the AMI evaluation set. So this justifies the formulation of this problem in this graph partitioning terms. That was about the graphical formulation. Let's look at how DOVER solves this problem. What DOVER does is it does a greedy selection of maximal cliques. So in step 1, it enumerates all the maximal cliques and computes their edge sums, and then greedily selects the cliques in decreasing order of weights until all the nodes have been assigned to some clique. So this on principle seems quite easy, but it's actually an exponential time algorithm because there can be an exponential number of maximal cliques in the graph. And so enumerating them and computing their edge weight sum is of course exponential time. We can also empirically see the implications of this exponential time method. And it means that as the number of hypotheses that we want to combine increases, the label mapping time increases exponentially. So this is a log linear curve, and the curve is linear. And it's also, the limit is reached faster for recordings which contain more speakers. So in this case, you can see AMI, which has 4 speakers, is under LibreCSS, which has 8 speakers. And for LibreCSS, the limit was reached just for 7 hypotheses. So we could not combine any more than 7 hypotheses in the case of AMI. However, as I mentioned earlier, DOVER was successfully used in Die-Hard 3 for combining a small number of systems, so like 3 or 4 systems. And in general, it provides quite a bit of improvement. So as shown here on AMI, it's more than 1% absolute better than the single best system that is being combined. So we do want to retain the performance of the overlap, but we do not want to spend an exponential cost in performing this combination. So we want something which lies in the middle. So how can we avoid this exponential complexity without sacrificing performance? To see this, let's take a step back and see how DOVER works. What DOVER does is it does a pairwise combination of hypotheses. So it takes 2 hypotheses, maps them using the Hungarian method, and then keeps doing that for all the hypotheses. And this is, of course, linear time because we are combining as many times as there are hypotheses to be combined. So as you can see here, finally, after all the combination, hypothesis A, B, and C would have the same underlying speakers, and so the voting stage can be performed. However, this creates a problem, which is called the anchor problem. When we are mapping, we do not know which hypothesis we want to map all the others to. And what DOVER does to solve this is just chooses the hypothesis which has the lowest average DER to all the other hypotheses. In this case, for example, if hypothesis A is that hypothesis, then both B and C would be mapped to hypothesis A. But this is an arbitrary solution, and it does not provide any guarantees. What we modified in this algorithm was to introduce a graph merge operation. So what we do is we do not choose any anchor. Instead, we start combining, for example, A and B, and after this combination has been performed, we merge A and B into a combined hypothesis AB, which is formed by taking the union of the underlying combined speaker nodes. So for example, if A1 and B2 were merged into the same speaker, then we'll create in the new hypothesis AB will have the new speaker node A1, which is just the union of A1 and B2. And
hey, Desh,
we
you're
keep
reaching the 2-minute mark. Can you please? Yeah.
Oh, okay. I'll hurry up. So this graph merge operation enables us to perform this combination very effectively. And this also means that the combination, the method, is now linear in time instead of exponential time. We found that adding this merge operation also performs better than the base Dover algorithm. So as you can see, from 27.9 to 26.3 diarization error rate. I'll skip over these. And adding this modification also enables us to provide a theoretical guarantee on the solution. We can also find approximations with tighter bounds. I won't go into the detail here, but we have an algorithm based on randomized local search, which can be used to show that we can obtain solutions with near optimal guarantees and with high probabilities, and which also empirically performs better than the linear time overlap algorithm. All this code is available in this QR code, and you can check it out and use it in your diehard submissions. Thank you.
Okay, thank you very much, Desh. We are a little bit short on time, but if anyone has a real quick question, I guess we can take it. Yeah.
And I'll also stay around after, so if we don't finish questions, we'll take them after, but go ahead.
Okay. Thanks for the talk first. Hungarian algorithm map to strings, best mapping. So you map between system 1 and 2, and then they combine with system 3. So if you would start it with another, combine B and C, and then A, you will have another result. Can you do some optimization to find what is the best way to start to combine them?
Right. So Desh, any experiments in experimenting with the order?
I see. Yeah, so what we do was we just randomize the order so that the output is not dependent on what order we are combining in. But in general, we saw that there wasn't much difference regardless of what order we combined the hypothesis in.
Right.
The merge operation really kind of normalizes all those differences.
So empirically, compared to Stolke's way of merging them incrementally, if you create this merged hypothesis, then the order seems to matter less. You're correct that theoretically you will get slightly different alignments, but in practice it doesn't seem to matter if you do that merging of the costs.
Okay, thank you very much. There is another question online here, but probably you can look at it and answer it.
Yeah, Desh, can you take care of it online?
Move on.
All right.
To the next paper.
Thanks.
Sure, I'll do that.
Thanks a lot. Really nice.